Hello, everybody. This is your professor, Daniel Slavati, and this is the first recording that I'm making, so this will be a short one, just to finish up our discussion of Section 8.3. So, to begin, let's recap what we have gone over already on Tuesday. Given H a normal subgroup of G, remember, right, we use H less than or equal to G to mean H is a subgroup of G, and then there's a little triangle there instead to mean H is a normal subgroup of G. And this, G mod H, it's called. So, say G mod H is the set of all left cosets or the set of all right cosets. And you should specify which. The book uses right cosets, but it doesn't matter because with a normal subgroup, right, left cosets are right cosets. Right, this is not true in general. A normal subgroup is one that satisfies this for every little g in G. All right. So we went over this theorem before, so I'll just say it again quickly. Given that H is a normal subgroup of G, this operation, coset HA times coset HB equals coset HAB, is a well-defined multiplication operation on G mod H, which forms a group with identity element H, and the inverse of coset HA is the coset for A inverse. So we went over a proof for that, and it's just a bit of a slog, but it all works out. Remark with additive groups, okay, with additive groups, so that notation above is for multiplicative groups. With additive groups, when additive groups are used strictly with commutative groups. So every subgroup is normal in a commutative group because this is always the case, right? Because you have commutativity. With non-commutative groups, you can have this being true. But with commutative groups, it's always true. So every subgroup is normal with commutative groups. And when your group is additive, you write your cosets this way, like how we did with ideals and rings. And then G mod H is an additive group with the operation coset H plus A plus coset H plus B is the coset H plus A plus B. Identity element H equal to H plus 0. And the negative or additive inverse of H plus A is H minus A. All right, so we did some examples last time. Let's go over them again. D2n, that is the group of symmetries of the regular n-gon. Okay, so regular triangle, regular four-gon, the square, regular pentagon, hexagon, what have you. And then that group has order 2n. There's 2n elements. There's rotations, 360 degrees over n, and then square it, cube it, all the way up to n minus 1. The identity as well. And then you have one reflection, b, and then you have rotate, reflect, rotate squared, then reflect, so on and so forth. So there's n rotations in the dihedral group of order 2n and n reflections. Okay, as usual. This set of rotations is a subgroup whose index is 2. Okay, so it's a normal subgroup. We proved that last time in section 8.2. A subgroup of index 2 that only has 2 cosets, it has to be normal because there's only 2 cosets. So the 2 cosets are of R, the rotation subgroup, just R itself, the coset of the identity element, right? R1 equal to just R. And then R times B, where B is that one reflection, or you can use any other reflection. And that's the set of reflections, right? It's 1 times B, A times B, A squared times B, all the way up to n minus 1 times B. And that's the multiplication table for the quotient group, D2n mod R. It's a group of order 2, so we know it's isomorphic to Z2. Now you have 2 elements, R and RB, R and RB. R times R is R times RB is RB. RB times RB, right? RB times RB is RB squared, but B squared is 1 because B is a reflection. So that's just R. Right? So it's just like, isomorphic to Z2. Right? That's a multiplicative group. The additive group, Z2, you got 0, 1, 0, 1, right? And you're adding. Right? So, right? 0, 0, 1, 1. Yes. Okay. All right, and then here's a nice example. Take the quaternion group of order 8. Okay, so that's the group elements 1, minus 1, I, minus I, so on and so forth, where I times j is k, j times I is negative k, using this triangle mnemonic. D, 1 comma negative 1, that is a subgroup of order 2, and its index is 4. And it is a normal subgroup. D8 is a normal subgroup, and you can check it. Right, I times D is the set I, negative I, which is the same as the set D times I. Same thing for J and K. So that's one reason. Another reason is because D is the center of group Q8, which we'll go over the center again. We talked about it before, but we'll go over it again. It's an important concept. There's one more theorem in the section I want to do, and that has to do with the center. So this is a nice warm-up example. All right, anyway, so Q8 mod D, it's a group of order 4, because there's 4 cosets. D, Di, Dj, Dk. All right, and here's the multiplication table. I could leave those, I guess. And, right, so for example, dj times di is dji. J times I is negative k, so that's d negative k, which is the same as the coset dk. Right, so there it is. And this is isomorphic to Z2 cross Z2. Remember, up to isomorphism, there are 2 groups of order 4. There's Z4, the cyclic one, and Z2 cross Z2. All right, every non-identity element in Z2 cross Z2 is order 2. And in Z4, you have elements of order 4. But as you see, everything has order 2 here. D squared is D. Di squared is D. Dj squared is D. Dk squared is D. Right? Di times Di is Di squared. I squared is negative 1. Negative 1 is in D, so that's the coset, D itself. So everything has order 2, so that's isomorphic to Z2 cross Z2. Of course, Z2 cross Z2 is an additive group. That's a multiplicative group, but they still are isomorphic. All right. Well, this was a nice example. Consider the additive group of rational numbers and the subgroup of the integers. Okay, because it's a commutative group, it's a normal subgroup, so we consider the quotient rationals mod integers. 2 cosets ZA and ZB are equal if and only if, remember 2 cosets in the multiplicative notation, HA equals HB if and only if BA inverse is in H. So here this is when B minus A is in Z. So 2 rational numbers, 2 rational numbers have a difference, will differ by an integer if and only if, when looking at the rational numbers over a common denominator Q, right, P over Q and R over Q, that's equal to their difference, B minus A, is an integer when the numerators P and R are equivalent mod Q. Right? So in particular, what you could do, okay, for any rational number p over q, there's a unique integer between 0 and q minus 1, so p less than q. Using the division algorithm, right, you have a unique remainder when dividing p by q. You get this unique remainder r. So you can always take that for your coset representative, the thing that you're putting next to the z. So z plus p over q is equal to z over r over q, where r over q is between 0 and 1, not including the 1. Q mod z is z plus a, where a is a rational number between 0 and 1, including 0 but not 1, rather than just z plus a, where a is any rational number. Yeah. So now suppose that a is between 0 and 1, and p over q is in the lowest terms. A fraction in lowest terms, that's when the numerator and denominator are relatively prime, right? For example, 6 over 8 is not in the lowest terms because they have a common factor of 2. So you reduce it to 3/4. Now it's in lowest terms, right? So suppose you have that in lowest terms. Let's try to find the order of z plus a. So q mod z, that's an infinite group. That's an infinite group, right? It's any rational number between 0 and 1 you can pick to give you a coset. So it's an infinite group. You notice it's an infinite group. Is infinite. But every element in this infinite group has finite order. Interesting example. Every element in the infinite group has finite order. Right? Try to find the order of z plus a. Well, it's the smallest positive integer n, such that n times z plus a, which is z plus na, is z. That is, for any rational number a, what's the smallest number n, such that n times a is an integer. Right? That is the smallest number n, such that na is in z. Well, this must be the denominator q. Right? Q times a is q times p over q, which is p, which is in z. And that's the smallest such integer when p and q are relatively prime, right? I mean, again, the same example we had before. What was it? It was 6/8, right? When you multiply it by 8, you get 6, right? But 6/8 is not in the lowest term. So actually, when you multiply it by 4, you get 6 over 2, which is 3, right? Because it wasn't in lowest terms. When it is in lowest terms, then q, the denominator, is the order. So every element in q mod z is finite order, but q mod z is the order of q mod z itself is infinite. The same cannot be said for r mod z, right? So, for example, z plus a has infinite order when a is irrational. In particular, square root 2, pi, etc. Okay? All right. So one more theorem, and then that'll be it for section 8.3. Then we'll go over some, in a different video, we're going to go over some of the problems in sections 8.2 and 8.3. Okay? So, all right. Recall the center, the definition of the center of a group. So recall that ZG is equal to the set of all A in G such that AB is equal to B all BA for all B in G. So in a commutative group, the center of the group is the whole thing. But for a non-commutative group, you do always get some center, like the identity element satisfies this. the identity element is in G, and the identity element commutes with everything else in the group. Okay, so like for example, you can have more than the identity element. Z of the quaternion group of order 8 was 1 and -1, and Z for D8, the dihedral group of order 8, that was 1 and R squared, where R equals rotation of 90 degrees. So rotating 180 degrees, and the identity element, that's in the center of D8. All right. Interesting theorem right here, and this will be used later to talk about groups of order p squared, where p is a prime. First, let's take the theorem. If the center of a group, I forgot. You'll also notice that ZG is a normal subgroup of G, because certainly AZG is ZG A for all A in G, right? For every A in G, because the stuff in Z commutes with everything in G. So it commutes with A. Okay, again, being a normal subgroup doesn't mean you have commutativity. It just means A times every element of the subgroup is equal to every element of the subgroup times A, but you may be switching elements to get equality there. But with this one, just naturally commute with everything. So it's a natural normal subgroup. And the theorem is this. So it's a normal subgroup, and then if G mod ZG is cyclic, then G is commutative. Okay, or I guess it's maybe a little bit more interesting when you say it in the contrapositive. If G is non-commutative, then G mod ZG is not cyclic. All right, so for example, the example we did with Q8 above, right? So the center of Q8 was 1 and -1. And we know Q8 is not commutative, right? I times J is the negative of J times I. Right? I times J is K, J times I is -K. So it doesn't commute. It's non-commutative. So you can't expect the center to mod out with Q8 and get you a cyclic group, but it doesn't, right? Because Q8 mod D, where D was that 1 and -1, it's actually the center of the group, is a group of order 4, and it wasn't Z4. There's only two groups of order 4, right? Z4 and Z2 cross Z2. This guy is cyclic, this guy is not, right? So since it was non-commutative, Q mod the center of Q, better not be Z4, better be Z2 cross Z2, and hey, lo and behold, it is. Right? So let's prove that in general. Right? If G mod Z is cyclic, then G is commutative. Not a hard proof, but we will do it. Interesting proof. Kind of a funny story. I remember just kind of thinking back when I was your age, when I took this class, how neat a proof it was. It didn't seem like a natural statement, and I found the proof to be very interesting. So maybe you will too. Here it is. So assume that G mod ZG is cyclic, right? Say that G mod, so ZG is generated by the coset, or right coset. ZG, let's do this. Let's do this. Let's just write ZG just as Z. So for this proof, denote ZG by just Z. Okay, so assume that G mod Z is cyclic. Say that G mod Z is equal to the subgroup generated by the right coset ZA. So that's 1 ZA, or not 1, but Z. ZA, remember the identity element is the coset, is the subgroup Z itself. ZA is 1 coset, ZA squared, ZA to the third, so on and so forth. And it could be infinite, right? Could be an infinite cyclic group, and that's fine. In which case you'd need ZA inverse, ZA squared, so on and so forth. Okay, so take A times A and B in G. Okay, we want to show that A and B commute. Right, so A is an element of, or no, I can't use A. Let's do X and Y in G. Say that X is an element of ZA to the I, and Y is in the coset ZA to the J. Okay, every element of the group is in some coset. Right, the cosets partition the group. Right, so X is in the group G, Y is in the group G, so it's in some coset, and Y is in some coset. Maybe the same one, maybe not the same one. So, but the cosets are to the power of A. So therefore, there is Z1 in Z and Z2 in Z, such that X is equal to Z1A to the I, and Y is equal to Z2A to the J. Right? Of course, because Z1 and Z2 are in the center, Z1 and Z2 are in Z, which is equal to the center of the group. They commute with everything. With A, and of course, A commutes with itself. Come on. Right, so X times Y is equal to Z1A to the I times Z2A to the J. Right, Z1 commutes with A, Z2 commutes with A, and A commutes with A. Right, A times A is equal to A times A. So powers of A commute with themselves. So whoa, you can just commute these guys. A to the J, Z1, A to, right, so I mean, you don't have to do an association here. So Z1, A to the I, Z2, A to the J is equal to Z2, A to the J, Z1, Z2, A to the J, Z1, A to the I, which is equal to Y times X. And that's it. Pretty cool. All right. So we'll use this theorem later. One of the things we've been doing in the class, right, was keeping track of groups of a given order, small order. There's one group of order 1 up to isomorphism, one group of order 2, one group of order 3, two groups of order 4, one group of order 5. Well, for any prime order, there's only one group. Two groups of order 6, Z6 and D6 or S3. One group of order 7. There's actually, I think, 5 groups of order 8. We'll get to that. But then, so later we'll use this theorem to prove that any G of order, I should turn that off. Any group G of order P squared, where P is prime, is isomorphic to ZP squared or ZP. So either you're cyclic of order P squared or ZP cross ZP. So for example, like groups of order 4, there's only Z4 and Z2 cross Z2. But same thing with 9, groups of order 9, there's only Z9 and Z3 cross Z3. Pretty cool theorem, and we'll use this theorem to prove that. Okay, so that's it for this section. So go to the video that is going to go over homework problems, discussion problems in sections 8.2 and 8.3. I will continue to communicate with you by email, and I will be available to you on Pilot during the usual lecture time for discussions and questions. More on that in the email. Okay?